Okay, welcome everybody. I think the stream of incoming people has kind of dwindled. Let's see whether we can start. My name is Roland Kuhn. Most of you might have seen me as Akka Tech Lead, but I've not been doing that for more than a year now. I'm a CTO and co-founder of Actix, a company who does IT for the manufacturing industry. So when we push to prod, it has a much more tangible meaning than in many other cases. But that's about all I'm going to say about what we are doing. We are concentrating on distributed computing, Akka Typed as a tool for modeling that, and some difficulties that arise, and then finally about how to tame some of these difficulties using formal protocols. Just as a reminder, please rate the session so that I can also learn something of the experience. Also, if you have comments, always welcome. And then, before we begin, just a reminder, finally, after 4 years of writing, this February the book was published, and you can now actually buy the paper copy. So there's this rebate code. If you don't want to spend 100% on it, you're welcome to. So let's start. First of all, we need to look at what is distribution. Can I see a show of hands? Who of you would be able to give me a definition? I'll not ask you to say it, right? Who thinks they could define what distributed computing means? Few hands, yeah. And who here has a feeling of, okay, what is it roughly? Why is it so difficult? It's usually a bit more, yeah. So I think, in my view, this can be split into two parts when it comes to trying to describe why it is hard. Now, distribution is hard, that's what everybody says. What are the two hard pieces? The first thing is, when we distribute something, it runs in two different locations at the same time, which means concurrently. It's inherently concurrent. Concurrency is a property of distributed computing. It comes with the package, so to speak. Concurrency means that an activity can be going on over here and over there, and time-wise, they overlap. It does not need to mean that they actually are executed on different CPUs in parallel. Node.js, single-threaded, also has concurrency in that sense. You start something, and you start some other thing, and then both go on, and then one finishes, and then the other finishes. The trouble here is, of course, if things go on concurrently, then you cannot really be sure beforehand in which order things happen. So we'll talk more about the difficulties later, but this is kind of the first half. The second half of distributed computing is as painful as it is necessary, and that is partial failure. If you do not have partial failure, then that means if some part of the system fails, then the system as a whole fails. This was true if you had a computer in the 90s with a single processor, single core. If something doesn't work there, or it goes into an infinite loop, nothing happens whatsoever. The whole system is stopped, cannot produce an output. So you only have total failure. This is not what we want. We want to build resilient systems, so we want the system to be able to survive as a whole when a part fails. That's the whole deal. Of fault tolerance, of redundancy, and so on. So partial failure is very much needed. But partial failure is also very problematic because, well, some part of the system keeps running and the other part is not running. It's distributed, you only have messaging. It's difficult to figure out when this case has happened, even. You need timeouts, you need heartbeats to detect that. That takes time, takes effort to get right. You cannot be sure whether the other VM, for example, is just doing a garbage collection pause of 5 seconds or whether it has crashed, so you need to wait long enough. So partial failure is the other hard thing that makes distribution even more difficult than a concurrent system. So this is what we are up against. Now let's see what tools we have. Well, obviously, I was going to talk about actors because that's what I like. I recently realized something about actors. I used to say that informally, actors model distribution. That's what they do. I realized recently just how exactly true that is. There is nothing you can fit between these two concepts. Actors model exactly what it means to be distributed. And that is something I learned when I tried to implement PyCalculus-based abstraction for writing composable behaviors in actors, when I noticed, oh, these channels that you can send around, so PyCalculus is also for distributed systems, but you can send around these channels on which you read, and then you have multiple readers for a single message, means coordination and so on, which means it's not the same kind of distribution, the same kind of availability or simplicity that you get with the actor model. With the actor model, you don't need any coordination to do the basic operations at all. The basic operations, just to recall, in response to a message, the actor can send messages, create actors, change its behavior. So that's the actor model. It's very short, concise, and it describes exactly what it means to have a distributed system. Now, there was once a post by Paul Cusano saying, I think the title was, the actors are too non-deterministic or something like that. I don't recall the exact title, but that's kind of the point. Concurrency in itself implies non-determinism. As I said, we have things that go on at the same time, possibly different locations, overlapping in time, and the exact ordering of the instructions that are executed by different CPU cores, for example, cannot really be foreseen. It might be that this actor here completes the step first and sends the message over here, or that actor, they are in a race condition, and we need to run the program on real hardware to see who wins, and we cannot possibly predict it. It goes down to quantum physics, if you will. So, I mean, it's really non-predictable what is going to happen in terms of concurrent processes and when they do their externally observable effects. This is bad. We don't like that. So, when we write a test, for example, we have a list, we generate some lists, and we have a sort function, and then we have a test that says, after sorting, the list should be sorted. That's completely deterministic. There is nothing random, nothing unpredictable about it, and that's how we like to program. Functional programming is all about composing operations on values, and we really like this to be completely predictable. We carry the effects that do not completely fit into this pattern to the end, and so on. This I/O monad that the previous talk described with the Monix tasks and so on. So we really value the determinism in our programming. On the other hand, who here has worked in e-commerce systems? Yeah, many people. It is not at all predictable who will buy exactly what at which time. The order in which we receive the orders from customers is completely non-deterministic, and we're totally fine with that. Is that not true? Yeah, we get these requests, we write a server that accepts incoming things, and we cannot prescribe the order. So in some cases, we are okay with non-determinism. In other cases, we are not so okay. Anyway, so non-determinism means you need to write tests that rely on timeouts, that might fail spuriously, and so on. It's not nice. But there is more. Concurrency is only the first half. Distribution implies even more non-determinism, because failure, partial failure, is by definition not predictable. If it was predictable, then it wouldn't be a failure at all. Then it would be an expected state of the system. So our system can do more interesting things that we cannot predict. So, yeah, how do we deal with this? In the end, what we want to do is we want to impose order. We cannot order all the things, we know that, but we want to impose as much order on the system as we can, to understand as much of it as we can, and then be as confident as we can that we do the right thing. So we want to restrict the amount of non-determinism. Now, there is a wonderful tool given to us by the universe that helps. It's called causality. Causality is awesome. Yeah? I send a message, and it can only be received after I have sent it. This violates the true randomness in that these cannot be reordered. Yeah? First I send it, then it's received. That's awesome. we build on that in many cases. Time runs forward. I mean, that's what this means. We couldn't have a conversation even if this wasn't the case. I mean, it would be completely confusing if Patrick answered before I asked. So that's not how it works. So causality is awesome. So we can use that, and some causality comes natural even when programming. It is ingrained in some of the patterns that we use. For an example, we look at an Akka Typed API that is called the Receptionist. These APIs are described in terms of message types. Actors are described by the messages that they handle. I don't need to give you the implementation of the Receptionist. This is basically the API that you'll use from the outside. You can send commands, and this Receptionist will then offer the service of registering an ActorRef that accepts a certain type of message, T here, with a service key for that T. Basically, it means there is an entry point into the protocol that's of type T. That's the first kind of message that you can send, and you can associate all the actors that you have in your system, in your cluster, for example, that accept that kind of message, tell the receptionist, and then someone else can find them. That's the purpose. So here we already see causality at work. When you send a register message, you include a reply to handle. Yeah, when you send it, it will then afterwards be received by the receptionist. And then the receptionist will put some things in some maps and so on, and send back a message to this ActorRef of type registered. The registered message then says, okay, this registration was successful. The registered message cannot possibly be transferred before the register message has arrived. Yeah, causality again. So this is naturally ordered. It cannot be done wrong. We can even push that further with something that is not yet in the API, but maybe should be there. So if the registered had another handle in there, which is an ActorRef for unregister commands, then we could later, when this actor stops serving this kind of request for some reason, send the unregister to the receptionist and then get back an unregistered later. So now we have a 4-message exchange that is completely bound by causality. You cannot send the unregister at first. It doesn't extend command. You need to really do the register, get the registered, and then you can unregister. Yeah? This cannot possibly be done wrong. But there is something that can go wrong. For example, someone could try to find services for a certain type, and none of them have registered yet. A cluster starts up, everybody does lookup, everybody does registration. The order in which this happens is not defined. So when you look up too early, you don't get any responses. Okay. So yeah, not everything is fixed by causality. And if things are not fixed, you need some sort of coordination. In this example with the cluster startup, you would first register all the services, then you would converge on the state and put that in some sort of, you could put that in CRDTs even if you want. Then everyone can see that this first phase has finished, and then they can ask for the lookups, and that would be coordination. But coordination takes resources. It has cost along multiple axes. It has cost in terms of code complexity. You need to design an algorithm, you need to implement it. It has cost at runtime. It introduces potential for more failures, and it can also affect the availability of your system. For example, if you use Paxos to obtain consensus on something, if too many nodes fail, you have a split network or something, then the Paxos algorithm will just stop serving results because consensus cannot be guaranteed. So coordination has a cost in many ways. We would like to avoid that where we can. Now, there is a very simple way to avoid coordination. If you know something up front, then no coordination is needed, obviously. Yeah, we kind of assume that 1 + 1 is 2, and that's built into all our programs. We don't need to coordinate on that. That's a very simple example. But I can give you a more useful example in trying to motivate how we should implement the cluster receptionist once we get around to actually doing that. And that is, we can use the fully qualified class name of these service keys as identifiers. And this fully qualified class name is fixed at compile time. There is no runtime coordination needed. Well, of course, you would need your teams that do the various services or actors to coordinate on a namespace, and everyone picks a name. So the coordination is pushed to the development phase, but at runtime, no coordination needs to happen. Then if you have that, the local resolution, so you give the service key to the receptionist can serialize that by using the fully qualified class name and talk to all the other receptionists in the cluster, but the local resolution still happens with all the right types. So this is cool. And then this talking among the receptionists in the cluster can use a CRDT map for disseminating knowledge who is where, because I don't believe that service lookup is something that needs to be sequentially consistent. I mean, etcd and Zookeeper and all these things are not really needed in terms of the guarantees that they provide. They are too strict, I think. So this would suffice for service discovery within a cluster. So that's cool. We looked at causality, but, well, causality is not enough. I'm going to, this is weird colors. So I'm going to show you an example to motivate what I mean with that. So it's a payment that we want to do using a payment gateway with an audit that we also need to perform. So the idea is that we have, again, I'm just showing the message types to describe the protocol. We have an audit service. There's a service key for it, so it can be looked up. It has basically a request-response protocol. You can log an activity, and then you get back confirmation that the activity has been logged. Plain and simple. Yeah, so we can do audits. Then we have a payment service. Someone once told me that these are the 4 usual operations, so I just copied that. Makes sense. So first, you have to authorize a certain amount from a certain customer's credit card. I put in here a UUID that is then associated with this authorization. Then there is a captcha message that can be invoked at arbitrarily later time that references this UUID and may use up to the reserved amount for doing the actual payment. Then there is void, which could, well, void an authorization or a refund for paying back the money. Now, how would we implement this using Akka Typed? No, I forgot the payment result. So we have payment successes, rejects, and ID unknown, so error cases. So how would we implement that in Akka Typed? So who here has looked at Akka Typed? Who has actually written code in Akka Typed? So it's just a few. So I'll do the crash course. I kind of assumed that would be the case. So this is a normal actor. It's a greeter with a counter so that there is some state, and it will tell you, hello, world, you're number 1, 2, 3, 4, and so on. So how do we translate that into Akka Typed? First of all, we need some different imports. The important one is now not Akka actor, it's Akka Typed behavior, and there is a DSL for constructing these behaviors, which is an Akka Typed Scala DSL actor. And this is basically a transcription of what is on the left, only now there is no var anymore, because Akka Typed clearly suggests or strongly suggests that you use immutable behaviors. You can create an immutable behavior by using actor.immutable, which takes a function. The function gets 2 arguments. The first is the context, the usual things you can do, watch, unwatch, spawn for creating actors. You can get access to the system, to the scheduler, and all these nice things. And the second one is the message, which is of type greet here, because everything is nicely typed. We print the expected message, hello world, you're number 1, and then we need to return the next behavior. As I told you, actor model, yeah, third part of the actor model is you need to return the next behavior. And Akka Typed really enforces that. So here we just create a new behavior with count plus 1, and the thing goes on. So, clear so far? Yeah? Good. So we can actually use this to implement some actors. Here we need some more tricks. So I can explain that here, because before waiting for the first message, this do audit actor needs to do something. The job of the do audit actor is to first send the message to the audit system and then use a behavior to wait for the response. That's what we do. So first we pick a random ID, then we send log activity, then we schedule a timeout message, which is a bit naughty here to fit on the slide. And then we return the behavior that shall actually be installed. This checks whether the message is the timeout message using this null trick. And then it checks whether maybe it was the reply to a wrong command, something got mixed up. If everything is fine, then we send the confirmation message, audit done, to whoever tasked this actor with this job. Yeah? So this is a step in the process that's factored out into one actor. The next behavior of this actor is nothing. The job is done. Yeah? So actor.stopped means this actor is now terminated. Second actor, do the payment. Something I forgot to explain on the other slide. Yeah, maybe I do it. No. This one will just crash if something unexpected happens, explicitly with an illegal state exception, so that the parent knows that it has not terminated successfully. We'll look at how that looks like. Then the do payment is basically the same structure, only it needs to do 2 steps. Yeah? We again use actor deferred to first do something, which is the authorize command to the payment gateway. We also schedule the overall timeout. And then we return a behavior that waits for a payment success. That's for the first step. Then we send the capture to the payment gateway. Again, return the next behavior. That's the inner actor immutable. If it's a payment success with the right UUID and so on, then we reply that the payment has been done to the other actor that gave us this task. And then this actor is stopped. And when something happens that's not in here, so this is just the happy case. Yeah? If something happens that is not in here, so wrong UUID or no success, the actor will just die with a match error, which is fine. I mean, we could do more refined error handling if we really want to, but this gets the job done because the parent notices, okay, the transfer has not really completed. So that's okay. Now we need a third actor that basically pulls these together, that orchestrates the process. Again, actor deferred, but now we do not send any messages. We also do not really receive directly the messages. We receive only the messages that, emitted from these 2 sub-actors, so audit done and payment done. And instead of sending the messages, we spawn these sub-actors. So you see their context spawn do audit for the pre-audit, which logs the starting payment. And this actor is watched. So when it terminates, we notice. We need to handle this terminated message. That's the same as in untyped Akka, because if you don't handle the terminated message, then the actor dies with a death pact exception. This is very much wanted if the child actor in this case has actually failed. But if it has not, then we can inspect the terminate messages that we get. And the code is not on the slide, but you can imagine this is just a case where there is a terminate where dot is failed is false. Then we handle it by just not doing anything. So we ignore successful termination. So after we have spawned the first actor and got the audit done message back, we spawn the second actor, and when we get the payment done back, we spawn the audit actor again with a different task this time. And once we get confirmation from that, we reply to whoever gave us the task. So, I mean, this is all problem decomposition, right? This is a reusable piece. So we reply that we're finished. Does that make sense? So this is nice, and it's much safer than in Akka untyped, because all the message sending, all the receiving of responses and so on is properly type checked. We cannot do the wrong thing in that sense. But it's not perfect. For example, what would the compiler say if I were to send this reply to message after the payment was done without doing the second audit? The compiler would not would be completely fine with it. There would be no error whatsoever. Or if we were to somehow invert the order in which we do the sub-steps, or if we were to forget the first audit, I mean, we can do lots of mistakes here that the compiler cannot catch. because there are side effects. And side effects are, well, invisible, so to speak. So in general, the problem is that causality works because it makes knowledge available only at a certain point in time, and then you can use that knowledge from then on. So time goes forward. First you did not have the knowledge, then you have it. But it does not force you to use the knowledge or to use it in the right order. That's basically the crux of the matter. So what do we want to do? Well, we would like to describe the effects and their ordering. So what ideally would we want to say? We want to say, first, this whole process, this actor, shall send the audit log and wait for confirmation. Then it shall send the authorize, get confirmation. Send the capture, get confirmation. Send the audit log, again, get confirmation. Yeah? This is what we want to happen. Now, we can write something down that is a type, that is a description of that. I guess most people have at least heard of the concept of HLists by now. This is just an HList. Well, it's kind of like an HList. I cannot use the shapeless HList because of reasons that you'll see later, but it's very similar. This _0 is the nil. It's the end of an HList. And the colon is the cons. So we have a list here of different types. And these types describe effects. This list says, first, this process, or whatever it is that we are describing, will send log activity. Then it says, we read the activity logged. Then, if you look at these actors in here, for example, this one, no, wrong. Sorry, I was jumping in the wrong direction, sorry. So, I have a detail in here that when the activity logged does not come back, so something unforeseen happens, the process may terminate. This is a choice, and the choice is modeled as a coproduct. This is the vanilla shapeless coproduct, where you can list different cases. C nil is the end of the coproduct constructor, and the colon plus colon is the, well, enumeration of the cases. In the first case, we have the halt effect, and in the second case, we have no effects. Yeah, so it may terminate or may not. So this list describes we do the first logging, and we do the payment, and then we do the post-audit. That's cool. Now, we would like to construct a program that emits something like this type so that we can check it. How would we go about that? For that purpose, I have been dabbling with various APIs, and what I'm currently liking most is this process DSL here, which is based on flat mapping and mapping, so it's kind of a monadic structure, but I wouldn't focus on the M word here too much. It's just a sequencing of operations. So this for comprehension says op process self is a value that is interpreted by an interpreter later, and when it's interpreted, it computes a value, which is the self-reference for this process. The self-reference for this process needs to have a proper type. And since we are describing the process to do an audit, we need to be able to read incoming activity logged messages. So this opDSL constructor up there creates a context in which the self-reference will be of type activity logged. Now, you see this implicit opDSL and the arrow up there? Yeah, I would really like to use Dotty at this point with the implicit functions there. They're going to be very cool. So, then the second line in the for comprehension, we have a send operation that takes the audit ActorRef and a message that fits the type of that ActorRef and describes the effect of sending the message. Then we have read and so on. Once everything has been done and activity logged has actually been received with the right arguments, so this is a filter operation that generates the possibly halt and so on. So when that all has been said and done, we yield the value that this whole thing computes, and that is done. Calling with timeout sets a timeout on this process. That the timer keeps ticking as long as this process is alive. If it's still alive after 3 seconds, the process fails. And the process is executed inside an actor later, and when a process in an actor fails, the actor fails. The reason for that is quite simple. If that was not the case, then we would have partial failure between processes inside one actor, which means inside an actor we have a distributed system, which would be mind-boggling. No, let's not do that. Okay, so the trick here is the return type. The return type of do audit includes activity logged as the self type of its process ActorRef, the done as the returned type, and it also includes the list of effects that are going to happen in the same notation. Second, we do the payment. I mean, this is basically the same thing, just with more steps and a more complex return type. Yeah, there's nothing else new here. But you see that instead of this kind of pyramid of doom-like structure that we had in Akka Typed with the immutable behaviors, we have this nice sequencing with the for comprehension. It's the same trick as with composable futures that basically get rid of this syntactic problem. Okay, then the third process to orchestrate these is one that needs to call these other processes. Calling a process is like calling a function. You call something and you get the value back. And this call happens in its own context. It has its own process ActorRef, which is decoupled from the caller's ActorRef, so that you can have these independent conversations going on. The audit needs to talk to the audit service and needs to understand that protocol. And the outer actor here, it doesn't actually need to talk to anyone, not to receive a message. So this says opDSL nothing, cannot receive anything. It just uses self as a marker of who's. So the audit will need to log the name of who did the logging. So once these 4 steps, first the pre-audit, then first the getting the audit service from the receptionist, then doing the audit, payment, audit. Once that is done, we send the confirmation back. And the awesome thing here is that we can write this method somewhere. It must not ever be called, doesn't need to be called, but once we write this method, it will look at this getMoney protocol object, that was this one, which has a type member called session, which it will extract. And then we have a call to getMoney, and the compiler knows what the return type of that is. It's this complicated type describing all the effects. And then this method uses simple implicit resolution to do a computation on these types to see if they match. And if you forget any of the lines, or if you just do something wrong, or send the wrong message at the wrong time, then this line will not type check. The compiler will tell you, you did something wrong here. There is one catch. I have not yet made this a macro, anyone is welcome to contribute. Currently, the error messages that you get are big. They are not really legible. They're very precise, but it can be improved in their usability, let's just say. But the goal has been reached. We achieved static safety on these things. So I'll spend the remaining time trying to look at behind the curtain a little bit, because I think that there are some interesting pieces. This is all inspired by work from Dominic Orchard in London, in Kent, I think, who has worked on these effect monads. It's kind of a graded monad, but I cannot tell you much more about it because I tried reading the graded monad paper and I had not yet the time to learn all the vocabulary that's needed to read the paper. So I kind of looked at his Haskell code and how he does it and mapped that to Scala. It took some effort and it actually is workable, it turns out. So what we can do is we can have a sequence of effects, that's the monad nature, so a sequence of actions. And all these actions are parameterized by effects, and then the monad takes these effects from the actions and is in turn parameterized. And this parameter is what we use to keep track of the accumulating effects as we build up the process. Yeah? So let's go a bit into that. I'll just show you a few things. Opsystem is an operation that computes or returns the system in which this actor is running. So this is an operation. The first type parameter is the type parameter of the ActorRef that in which context it is running, so which messages it could potentially be receiving. Opsystem doesn't care about that, but it returns a value of type ActorSystem nothing. It's ActorSystem nothing because down here in the hierarchy, we have no clue what the type of the guardian actor is. So we cannot send it any messages without further knowledge, hence ActorSystem nothing. And in the end, there is an _0, which means Opsystem does not emit any effects that we track. It's just an access to a field in a dictionary, if you will. That's different for opread. Read, again, also needs to be executed inside a context of an ActorRef type. And this time we really need this because we return opDSL.self, so the kind of message that we get from the input channel as the computed value of this operation. And it has an effect. It has the effect read of opDSL.self. Same goes for send, properly checking that the message fits into the target ActorRef, and then we say, yes, the effect is that we sent a message T. Now, effects. I told you shapeless HList was not quite enough. The reason is this loop. So otherwise, it's a normal just type level HList. It doesn't have a value level representation, as you will see. So there is a nil, and there is a cons, so the colon, which has a head, that's an effect, and a tail, that's a list of effects. And a loop is just something that has a list of effects that occur, well, in an infinite loop. That's the intention here. And now, how do we do this? This accumulation, that's the most interesting step. So here's the signature of the flatmap method. The operation has its self-ActorRef type S. We need to preserve that because, I mean, we live in this context. So we cannot break out of this context. It needs to stay the same. So S is the same throughout. Flatmap takes the computed value of this operation, this out, applies a function to it, which is another operation with the same S, but the different T of the computed type, and it may have different effects. Yeah? So this operation already had accumulated effects E, and then we flatmap onto that, so we sequence behind it, effects E1, whatever that is. Now we need to compute the concatenation of the two. So we ask for an implicit evidence of type prepend E to E1, which does this concatenation of the lists. And then we return p.out as the resulting effect type. This means the compiler can track the effects. How does this computation work? So this is basically mostly copied from Shapeless. This is standard inductive reasoning, basically, on lists. Lists are really a nice structure for that. So if we... Yeah, stacks. Okay, yeah, it's HStack, by the way, as Victor says. Just showing the prepend here, we want to prepend first to second, and there is a type out that will be a subtype of effects as well. And if we want to use multiple of these computations so flatmap just needs one of them, but if you need to use multiple of them and one needs the input, it needs to take an input that was an output of another. Well, unfortunately, we can't use this p.out trick because that only works after the closing parenthesis, and there can be only one implicit argument list. So this is what the aux pattern fixes, just makes it one more type parameter. And then, so we asked for an implicit prepend, and here are just the cases. The compiler will first look in the lowest. If we prepend something to the empty list, well, it's the something. If we prepend the empty list to something, it's again the something. And the prepend low case is the interesting one where we do the induction. So we take the head of the first list to the side, and we prepend the tail of the first list to the second list. Yeah, that's what we ask for. So we ask for an implicit ev prepend tail to the second, and given that, we know how to construct a prepend for the whole thing. And then the compiler will recursively go through the first list and figure that out. Obviously, there is no case for loop here, because what would it mean to prepend an infinite loop to some effects? That's not really meaningful. So you cannot do that. You cannot flat map an infinite loop construct, which will manifest in an implicit not found. So this is why there is this message, implicit not found. This only happens if you try to prepend an infinite loop first to second, and then you get even a sensible error message in this case. Yeah, that's cool. So talking about these loops, this is how it looks like to do a server-like process. A server process may do some setup actions, and then it enters basically an infinite loop and handles an unbounded number of requests. So this one just gets its self-address, registers itself at the receptionist under the name login service. Then it starts a concurrent process within the same actor, this op fork. There's also op spawn for creating sub-actors, creating child actors. So this fork creates the backend store, which runs in the same actor, and then we enter the infinite loop, which is, I mean, totally simplistic. Once we get a login, we automatically reply with an all success. I mean, obviously, you would need to authenticate and stuff, but this demonstrates the basic principle. Now, what is the type of this? The type of this is, well, this needs to read login and returns nothing because infinite loops do not return anything. And then the effects are that we read the registered from the registration at the receptionist, we fork that other loop, and then we enter the loop of reading login, maybe halting, because of the pattern match here. On the left of the arrow, there's the login reply to that always generates this may halt. And then we send all success, and then keep returning that and keep looping. Yeah, so these are some of the things. This is not all. In this project, there's also beginnings of a sketch of how to integrate persistence, how to access shared states using a state monad inside every actor. Actually, it's an unbounded number of state monads indexed by names. Fancy stuff, but the API is completely not finished or ready for production or anything. There is no binary release of this yet because it's pretty researchy. But I think there's quite a lot that we could potentially do. And I would appreciate any kind of feedback, or if you even want to get involved, that would be awesome. So it's in my own GitHub under Akka Typed Session for now, because it's just too researchy for the Akka repository at this point. Yeah, okay. Then with this reminder, I would like to thank you for your attention. Are there questions? You promised some heckling. There is a question, actually. Yeah, what's with the nulls? Yeah, I was lazy. No, so the thing is, if you don't want to use nulls, let me go back to the slide that actually is infested by them. Where was it? One of these, I think. Yeah. Yeah, so we would have to make another message that is the received, the timeout message, and it would be pretty painless in Dotty, because I could say this actor.deferred is of type payment result or timeout. Yeah? That would be so cool, but I can't do it in Scala 2. So this is why I hacked it using a null, because I didn't want to introduce all the wrapping that would otherwise be needed to make this work. It's a hack, sorry.
Hi, okay. So I just wonder, these behavior types looked, reminded me a bit of a CSP. Mm-hmm. Do you have any relationship there, or?
Yes, I am actually working with the ABCD group in Great Britain, who are working on session types. This has been the motivation for going in this direction, and Dominic Orchard also works in that group. The idea is the following: there is a way to formalize a communication protocol by saying which participant is allowed to send which message when, in what sequence, and where are the branching points, and so on. And you can write down the protocol. You could have a formal specification, for example, of the whole Paxos protocol, and then you make a projection of all the allowed interactions of the sequence of things as seen by one of the participants. This local projection is then a local session type, And that is precisely the thing that I'm trying to match against. So the idea is to use a tool like Scribble that can translate a session type into some other output. So there could be a Scala Akka Typed Session backend, and that would just emit this object which has the expected type definition, and then you write your actor, and then you use this vet protocol to bring them together, and then you get compile errors if you mess up, basically. Yeah, so there is a connection, thanks. If no more questions, then thanks again.